introduce Alok Laddha, also from Chennai Mathematical Institute. Without further ado, please, the floor is yours. Please go ahead with your talk. Thank you.
Oh, okay. Thanks, Saurya and Arpan also for inviting me to give a talk here. So I slightly changed the title of my talk. And so this is the new title. I mean, it's really the issues that I want to discuss are some of the open questions that we are facing right now in understanding classical and quantum observables in 4 dimensions when we have infrared divergences. Although most of my talk will be, focused on the classical observables. So let me just start with some broad motivation, which actually was very nicely covered by Raphael and Emil also in their talk. So, one of the most, of course, useful and fascinating quantities in gravitational physics is the waveform emitted during, scattering or in spiral of astrophysical objects. And this waveform, which, is like a 1/r component of the radiative field, and that is measured by a detector at some large distance and at some angle. And of course, it's it depends on the infinity of the multiple moment of the radiating source. And of course, computing this analytically is a nightmare, and because of which there have been the significant advancements in the last few years in able to, to develop tools to compute analytically these the waveforms. So in a generic scattering where objects like black holes or neutron stars, they start with some initial momenta, with some P1 to Pn, they can scatter, merge, or fragment, and into objects with different momenta. The only sort of really the zeroth order constraints we have is the conservation of linear and angular momentum, of these objects, plus the momenta contained in the field. And so these conservation laws, of course, are tied to the well-known fact that even though gravity is dynamical, at large distances, the space-time becomes flat. And so we have Poincare symmetry as a symmetry of scattering. But of course, these are finite number of conservation laws. So they don't really give us too much insight into computing this radiative field. So here the convention is that omega is the frequency of the field when I'm looking at frequency domain, and n is the direction at which we are placing the detector, and E is, of course, the metric. So just to give an illustration of how complicated the situation is, of course, we can start with a very simple example, which was worked out by Peters long back in 78, where he looked at a small particle of mass m, which kind of scatters at some impact parameter, in the background of a Schwarzschild black hole. There's a back reaction, and the particle emits radiation. And Peters rather remarkably gave us some analytic integral formula to compute this emitted radiation. So as you can see that I hope it's visible that it's a complicated sum of 4 terms, where he has gone to frequency domain and then at spatial distance x. And these are integrals which we cannot analytically, of course, compute. They depend on details of the trajectory of this particle, etc. So it's a very complicated intractable integral equation for E mu nu, which is measured by a detector in a band omega and omega plus d omega and angle n hat in the sky. And of course, the whole objective is to compute these radiative modes. And so, of course, the 2 schemes that we heard about in last 2 days a lot. One is the post-Newtonian scheme, which is remarkably powerful and old perturbative scheme. And it applies especially to systems like in spiral, where objects are far apart and move slowly. And it's of course, as you all know very well, it's an expansion in 1/c. And on the other hand, post-Minkowskian scheme, which Raphael reviewed very nicely, is a weak field expansion, which is valid when you don't have collision or merger, when the gravitating objects are far apart, but they can move with arbitrary velocities. And so, for example, gravitational scattering, where impact parameter is much larger than the Schwarzschild radius of these objects, then this is an excellent scheme in which we can try to do computations. And these are, of course, the 2 of the most famous schemes. And so, of course, then the schemes are, the parameters that are involved in the scheme are either low velocity or a roughly large impact parameter or large separation. But in this talk, I'm going to talk about a different perturbative expansion, which is interesting in its own right. And it's an expansion not in the properties of the system, but in the properties in some sense of the detector. So the idea is that you consider a detector in infinity whose frequency band is such that the frequency of the detector, resonance frequency of the detector, is much less than whatever is the characteristic frequency of the system which is gravitating. And so the detector is only sensitive to low frequency radiation. By low we mean radiation whose frequency is much less than the frequency of the system, and so it's called soft radiation. And so in this scheme that we will discuss, the perturbation parameter is really this the frequency the frequency of the detector divided by the characteristic frequency of the system, and it's called a soft expansion. And the one thing I will try to convince you is that it's remarkably constrained in terms of moment and spin of the initial and final objects, and it can be used as a very powerful tool in its own right. So let me just to give a very brief example. We could do the following. We could just go to the Peters computation for the radiative field and just do a soft expansion, because he gave us some integral expression, so we can just expand in this parameter. And it turns out that and I'm just writing down first two terms, and these are the two terms we find. So the first term goes as it goes as a pole in the frequency, which is 1 by omega of the detector. And it depends on the plus indicates the final momentum of this particle of mass small m, and p minus is the initial momentum. And so that term is completely fixed by the initial and final momentum of the scattering particle. And then there is an additional term which goes as log omega, and that term depends on not only the initial and the final momentum of the scattering particle, but in some sense initial and final momentum of the Schwarzschild black hole, which is fixed because we are assuming it's very heavy. So it is just, I'm just indicating that with mass capital M. And so this is schematically the formula that we find simply by taking this particular perturbative expansion of the Peters formula. And so the leading term is actually, of course, all of you very well know, and Paulomi also talked about it in the post-Newtonian expansion. It's this famous linear memory effect, which is what most well-studied radiative observable, or what I would often call event shape in the gravitational scattering. And then the sub-leading term, which is going to be the main for interest to us, is the logarithmic correction to the memory effect. And it's also, of course, a late time observable in the sense that we are assuming the detector is either kicks in at very late time or at very low frequency. And in the time domain, the second term decays as 1 by u in the retarded time, and it's called the tail to the memory. So here I just want to offer a small clarification that Paulomi also talked about tail to the memory, and in the post-Newtonian literature, that tail is often meant as it's a subset of terms that we consider tails. So maybe in discussion we can talk more about it. So these tails have something in common, but the tail I'm talking about is something that you see in scattering, which is more generic, which has more contribution than the tail that you see in the in-spiral problem. So of course, memory effect, as we all know, is a non-perturbative observable in the sense that it's something that is analytically we can it's an observable even in collisions or in merger. And it's just fixed by the initial and final moment of the scattering object. It doesn't require us to have a large impact parameter scattering or anything. And of course, it depends on the direction at which we are measuring the radiation. So it's not isotropic. In different directions, it has different values. And the one that from the Peters formula we found was just a linear, what we call linear memory. But in general, of course, in a collision where you have significant gravitational radiation also emitted, like in black hole mergers, then we get what is called a displacement memory, which is a contribution of, which is a sum of the linear memory and a non-linear memory. So just for completeness, I've written down this formula here, where the second term is the contribution of the gravitational radiation itself to the memory, which was computed by Christodoulou. And it turns out that, so of course, the natural question to ask is that, what about the log term that we found here? Is that also, is that just is just a typical of the Peters case, or is generically in scattering, we would find a term which goes as log omega and which only depends on the initial and final moment of the scattering particles? And it turns out that that is indeed true. And in a remarkable series of papers, Bishwajit Sahu, Ashok Sen, and their collaborators proved a class of results which are called classical logs of theorems. So I'll explain them in more detail in the next few slides, but in a nutshell, these theorems basically show us that when we do the soft expansion in the frequency of the detector, then there are various terms which are universal. That is, they only depend on the initial and the final states of the scattering objects, and their functional forms are completely independent of the details of the scattering. So whether you work with Einstein-Hilbert action or some high derivative terms, the form of these observables, these different coefficients do not change. And actually, this is precisely the aspect, this universality is precisely the aspect which made displacement memory such an interesting observable from theoretical perspective. And it's quite striking that, gravitational scattering, as we will see, potentially give us like an entire hierarchy of such universal coefficient in the soft expansion. By the way, I forgot to mention, please stop me at any time, because I have enough time to cover everything and also take questions in the middle. Okay, so let me, before explaining this Bishwajit and Ashok soft theorem, let me give you the setup that, we have a gravitational scattering of some initial objects like black hole or neutron stars, which have some masses m1 to mn, linear momenta, and some angular momenta or spin from j1 to jn. And then they scatter into some other objects of some masses and momenta, and some, of course, finite energy gravitational radiation. And our goal is to analyze, what is this outgoing radiation, the low frequency expansion, or in the time domain at very late time. So, okay, this is just the, if we had an impact parameter for the system B, then, we would either do an expansion in omega B, or if you had a massive object, a large mass object like Schwarzschild, then we could equally do a good expansion in omega by m. But the key parameter here is the frequency, resonance frequency of the detector. And so I just want to set up some convention which will be useful later. It's most of you will be familiar with it. Radiative. So these radiative modes of the gravitational field are, of course, transversal. And basically, if you when we study them, this we are really studying what we call a spin-to field at infinity, and this typically infinity is light-like separated from the sources, and so it's called null infinity. It's just a name, and topologically it's a cylinder. So it's this is the place where gravitational radiation hits. It's something which will be useful for us later. And as we discussed before, we are just going to indicate this. So these transversal modes, which depend only on the spherical components, I will indicate them as AB, E tilde AB, where AB corresponds to the transversal coordinates. And when I refer to universality, I already used this word before. I would simply mean a term in the radiation which is independent of the details of scattering and only depends on the asymptotic charges of the particles. So linear momentum, spin, and masses. And so if the term in the radiation in the soft expansion which depends on more than this, we will consider it not universal. And this just each such low frequency mode, like at 1 by omega log omega, we just call it event shapes. It's just a word for the low frequency observable that we use in QCD. So it's just a nomenclature that I have stuck to in this talk. So here is a schematic form of the soft expansion, and just for generality, I've written it in D dimension, where D is greater than or equal to 4. I will discuss the differences that arise between 4 and higher dimensions. So the expansion, if you take any D greater than or equal to 4, the expansion starts at 1 by omega, and then there are these logarithmic terms which I've indicated in blue, and then there is a omega to the 0 term which I've indicated in red, and then there can be terms which are polynomial in omega, or terms which are not of the form omega to the n log omega to the n plus 1, but of the form omega log omega, higher order. So for example, the blue terms are not the same as the final set of terms, which is, there's a question, I think, in the
I just wanted to know, the theory of gravity is you assuming only Einstein's theory, or whatever corrections that may come from quantum gravity, is it?
No, any classical theory of gravity. You can have higher derivative corrections and anything, non-minimal coupling. Yes. So we will call them theorems because we will call these theorems if these coefficients do not depend on the details of the theory. So those coefficients which depend on details of the theory, they are not, they are not of primary interest for us. So yeah, that's a very good question. So all the terms that I have suppressed here, like order omega log omega, in principle, they depend on the details of the theory. If you have Einstein-Hilbert theory, action, or some other theory, then their form will change. These coefficients, their functional form will change. Their dependence on initial and final momenta will change. Is that clear? Did I answer your question?
Yeah.
Okay, thank you. Okay. So, of course, as we discussed before, the first term in this expansion is what is called displacement memory, and is something that we all are familiar with. And it's universal in all dimensions equal to or higher than 4. And it's, of course, also independent of the spin of the objects. It only depends on the linear momentum of the scattering particles. The red term is interesting in its own right. It's a term which is independent of the details of the scattering in all dimensions higher than 4. Sorry, there's a typo. So in D higher than 4, this term is completely fixed by the incoming and outgoing momenta as well as spin of the initial and final objects. And it is sometimes called spin memory. But this object is often computed in 4 dimensions by ignoring precisely the effects which arise in 4 dimensions that we will discuss. So it is often, in literature, you may see that spin memory is also considered sort of a universal or a robust observable, but that really relies on the strong assumption that physics in higher and 4 dimensions is the same. And that's precisely the point that we want to discuss in more detail. But it is indeed true that this red term is universal in dimension higher than 4. In 4 dimension, it is it is no longer, if you really look at generic scattering, it no longer remains a universal term. But the blue terms are interesting because they only exist in 4 dimensions. And they have been explicitly shown to be universal if you consider the first 2 terms, which is n equal to 0 and 1. And they are really tied to simply the long range effects of the gravitational radiation. And the first, in fact, the first term in this series is precisely what we found when we just took Peter's formula and did a soft expansion, which was a log omega term. And so this first term is what is called tail to the memory in general for any scattering. And so these terms are really exactly like displacement memory. These terms are universal, and their universality was proved by in the series of papers by Vishwajit, Ashok, and his collaborators. The suppressed terms are related to what TRG asked. They are generically non-universal, and they depend on the details of the scattering. So if you change the theory, then these terms, the form of these terms will also change. So that's there's another question.
Sorry, one.
Yeah.
Since you mentioned it as one gravitational, the 1 by RFX. So the massive gravity will be excluded from this, is it?
Yeah, that's a very good point also. Yeah, if you have graviton is massive with however small mass, you will have no log omega terms.
Okay. Fine. Go ahead.
Yeah. And what is interesting about all these universal log terms is that they don't even depend on the spin of the scattering particles. They only depend on the momentum of the scattering particles. So they are really as universal as displacement memory. They would be same for a Kerr black hole or Schwarzschild black hole. And it has been conjectured that this universality for the blue terms, oops, sorry, I went forward. For the blue terms, the universality extends to all order in n. So this was conjecture which has been put forward by Vishwajit and Ashok a few years back. And just to say that, if you are wondering how these log terms go in time domain, so as we discussed, the first log, which is just log omega, its Fourier transform is just 1 by u at large u, and the second term, which is n equal to 1, decays as log u by u square at late time. So these are really logarithm. Even in the time domain, these are some log modes that will kick in at very, very late time after the scattering has taken place. And just really want to emphasize one thing, that the physical origin of all of these log modes is precisely simply the long range interaction between the scattering states, and of course also the curvature effects on the emitted radiation, which Raphael also talked about yesterday. And each term in this expansion is a function of the sphere. So it itself is like a 2-dimensional field on the sphere at infinity. And so it is quite remarkable that, we have this hierarchy of these fields on a sphere at infinity, and it is completely fixed no matter what kind of scattering we are looking at by the asymptotics of the scattering objects. So now obviously the question is that, can we derive this universality by simply studying properties of gravitational physics at the boundary? Because really these are boundary observables. They are radiation that we are capturing at infinity. And the fact that they don't depend on details of the theory tells us that they must be tied to some sort of a universal structure of gravitational physics at the boundary. So maybe I will, maybe this is a good time to see if there are any other questions, because we now move to the next part of the talk. Okay. Okay, so now here, to understand the underlying universality, possible universality of these different event shapes, there is an idea which has come in last decade or so, which goes under the name of infrared triangle, which is the following, that there seems to be a 3-way relationship which has emerged between seemingly disconnected ideas in gravitational physics. One is these low frequency radiative observables in classical scattering, which we call event shapes. One are symmetries of classical gravitational scattering that we will talk about. And one are, which seems completely far removed at the outset, which are factorization theorems that constrain quantum amplitudes, scattering amplitudes, that Emil and Raphael also talked about. And abstractly, this 3-way relationship, which have kind of drawn as a schematically in the figure below is what is called the infrared triangle, because all of these are infrared quantities in gravitational theory, some classical, some quantum, and so supposedly there's some evidence that we will discuss that they do seem to be very intricately related to each other. And for the purpose of the most of the talk, we will focus on the lower edge of this triangle, which is purely classical, where we will try to see the relationship between these event shapes in classical scattering and the symmetries of classical gravitational physics. And only in the end, we will discuss connection of these things with the factorization theorem in the amplitudes. So that's just what I said, that the relationship, of course, of the amplitude factorization with classical event shapes is a rich subject, and Emil touched upon it in his talk also when he talked about the soft modes that contribute to the conservative sector. But it's something that we will really just very briefly discuss in the end. So the goal in the rest of the talk is to understand how well the classical side of the infrared triangle is understood in 4 dimensions. And of course, the naive expectation has been that there should be, so this infrared triangle that I drew is kind of abstract. I mean, it's, just the 3 vertices of this triangle are just some abstract words. But naive expectation is that there are as many manifestations or avatars of this triangle as the universal event shape. So for each, there will be one infrared triangle for the displacement memory. There should be one infrared triangle for the tail to the memory, and so on and so forth. And so we would like to understand this side of the triangle. And in order to understand, unfortunately, we have to go back at least 60 years and revisit some part of mathematical relativity, which is where these radiative modes are localized, which is null infinity. I will be, of course, very brief about this, but if you have any questions, please stop me. So, in the 60s, as most of you will know, the relativists like Penrose, Bondi, and others analyzed a class of spacetimes in which gravitational radiation decayed polynomially in R. So if you look at Weyl tensor of gravitational field, it decays polynomially in 1 by R as you go at large R. And as this happens, as the spacetimes basically approximate Minkowski spacetime better and better. And of course, as we all know, gravitational field travels in null directions, in light-like directions. And so their decay at late distance and the emergence of flat spacetime at infinity is really manifest when you move in null direction. So the structure that comes at infinity then is called null infinity. And the spacetimes that we get by studying, where all the radiation is falling off polynomially in 1 by R and spacetime is becoming flat, are called asymptotically flat geometries. So this is some subject, most of which is above my pay grade, but fortunately, this is all we will need from the math GR literature, really. And I've just drawn a schematically a figure here, which shows that you have a null infinity, which we call Scri plus, where all the fields end. But if you have some massless field which is originating in the past, then it originates from what we call Scri minus, which is the past null infinity. And this is like a schematic cartoon picture of an asymptotically flat spacetime. And just to complete this brief discussion, these are both of these null infinities, past and future. They are cylinders, so they are parameterized by angles on the sphere, and either a retarded coordinate u for the future null infinity or advanced coordinate v for the past null infinity. And that, this is something you can easily understand by just looking at Minkowski spacetime and seeing how the retarded coordinate labels outgoing null lines and advanced coordinate, labels the incoming null geodesics. And the metric on this sphere, which is not the u and the v coordinate, is just our standard sphere metric, unit sphere metric. So if I just have a flat space-time, then and I look at future null infinity, then I have like a sphere metric and I have like a null coordinate u. But then when gravitational waves come, they disturb this metric at 1 by R order in the metric expansion, and this is the disturbance is typically captured by this tensor on the sphere, which is called C. And if you are not familiar with this, it's really just simply analogous to if you study Jackson's book on classical electrodynamics and study transversal components of electromagnetic radiation. It's exactly similar to that, but for gravity. And it's a data which is the data either in the past or the future is completely unconstrained. Of course, if I give you sources, then the data will be dictated in the future by the past data. But if I don't specify anything, I could start with CAB and the future null infinity and solve Einstein's equation everywhere in space-time. And in that sense, this is a free data, and it's called the shear field. And of course, we know that all these space-time, because they are Minkowski at large distance, they have Poincare symmetries. So then in particular, they have time translation. And interestingly, all the time and space translations can be completely nicely represented on null infinity. So for example, in future null infinity, which may be initially counterintuitive because U seems like time and you would expect only time translation to be nicely acting on U, but it turns out even space translations act very nicely as some kind of angle dependent translation, which depends on the first spherical harmonic. And so, just simply because of this point, how translations, global translations act, Bondi, Matson, and Sachs realized that, even if you consider more general translations of U, where the translation is by arbitrary angle-dependent function f, then they proved that the asymptotically flat space-time in, which, as we reviewed before, it doesn't change. And so these are really symmetries of our theory in the sense that they take one spacetime which is Minkowski at large distance and map it to a spacetime which still remains Minkowski at large distance. And the action of this F is not trivial because you can check that the shear, which is a physical field because that's a radiation at infinity, changes under super translation. So even though these look like coordinate transformations, they are really physical symmetries of the theory because they change the radiation field at infinity. And as an analog, similar things happen in electromagnetism where your radiation electromagnetic potential transverse mode of the electromagnetic field will change under a gauge transformation, which does not die down at large R. And these are typically called large gauge transformations in electrodynamics. And so just as a cue from Maxwell's equation, we can, if these are symmetries, of course, first thing we would do is to compute charges. And, if you consider if you consider the analog of global translation in electrodynamics, then it's the global U1 symmetry. And so the corresponding charge is a charge that you compute on a sphere at infinity, and that's the electric charge. And there's exactly a similar thing that happens with these translations, global translations in gravity, and the charge is something I've written there. So this F, remember, if you are looking at global translation, then F is either, if you look at time translation, then F is just essentially y00, and for space translation is the y1. And so for both of them, this is the total, this is either the total mass or the total linear momentum of the gravitational field, which is called EDM mass or EDM momentum typically. But it turns out that even for generic functions, we could compute these charges. And so then you can ask, okay, if these charges are computed, are they conserved in scattering? So you could compute them in the future or in the past, and you could ask if these things are conserved in a scattering. And this was a proposal that Strominger and the collaborators made more than 10 years ago. That, the point is that if you assume that we could start by assuming that the charges are conserved in a generic scattering and ask what are the implications of this conservation law. And even though this was initially a proposal, this was later proved into a theorem by a number of people in very beautiful papers. And the implication of this conservation law is what I have written below. So if you assume that these charges are conserved, which is what was assumed by Strominger and collaborators before that it was proved that these are really conserved. The implication of this conservation law between past and future null infinity simply is that the displacement memory formula. So I'm not, of course, going into the details, but if you just literally write down this conservation law in terms of fields at infinity, you get the equation that I've written in the bottom, which tells you that it reproduces the fact that the leading soft mode in the radiative field is completely given by fixed by the momenta of the scattering particles. And this, if you remember, this is precisely the displacement memory formula. So the conservation law is same as the displacement memory formula. So, even if we didn't want to go into the rigorous proof of the conservation, the fact that we know displacement memory is correct, observable, this proposal is vindicated by the independent results. So that basically is the first our probe into the first infrared triangle, which is kind of connecting the displacement memory in theory of gravity in a gravitational scattering with the conservation of these so-called super translation charges. Now the second term, now we can be ambitious and ask, okay, is there a similar interpretation in terms of some conservation law for the second universal term, which is the log term or tail to the memory term? But this term is of course independent of the displacement memory. It's just an independent mode. So is there a question? So if its universality were to be explained by a conservation law of gravitational scattering, it could not be super translations, because super translation already, conservation law of super translation already telling us that we get the displacement memory formula. In the BMS symmetry, the only other remaining part of the BMS symmetry is just a part of the Poincare which remains after we remove translation, which is the Lorentz group. And that would, of course, clearly not be enough because we know that the conservation of Lorentz charges simply tell us that the total angular momentum is conserved. But this log tail to the memory are far more nuanced things than just total angular momenta. So, of course, the natural question is that if we wanted to seek some sort of a symmetry which explains universality of this, even the first log mode, how do we go beyond BMS? And it turns out that now, the fact that the same universal structure of the log, which is encouraging us to look at some symmetry, actually comes and hits us right in the face. So as we discussed, that BMS proved that the symmetries, which was this infinite, this enhancement of Poincare symmetry by super translations, they derived it assuming that the spacetime sorry, I wrote it wrong. Spacetime satisfy Penrose's peeling property, not violate Penrose's peeling property. What this means is the following. So this peeling property, as we roughly discussed, is telling us that the radiation falls off polynomially in 1 by r. And we can be a little more precise about it, that if you look at what are called wild scalars, so there are these 5 scalars which completely contain information about the radiation in a gravitational radiation. These are, unlike the metric, they are gauge invariant objects. So sometimes they are more convenient to look at. And the peeling property tells us that all of them decay, as you can see, as some power of 1 by r. Like none of them, decay with some transcendental log terms or anything like that. So BMS used this property of the decay of these wild scalars to show that this super translations has the symmetry of the theory. But now it turns out that precisely in 4 dimensions, if you have massive particles which are scattering and emitting gravitational radiation, then this equation is generically violated. And this result is really not new. I mean, this result has been, although it remains a controversial result, it has been derived from different, using different arguments by Damour in 80s, then Christodoulou in early 2000, and then recently by Kerberger in a series of papers in last 5 years. I will just briefly discuss this argument because this is quite important for us. So here is a Christodoulou argument, which is very beautiful in my opinion, but also very simple to understand. So Christodoulou did a very simple toy example. What he did was he looked at a system of n massive particles, which are constituting to make a quadrupole source, and they scatter from the far past. And then we know naively that we know that the radiation will be given by quadrupole moment. And what he showed was that if you just look at the quadrupole moment formula and study this shear field, which is the radiation field at future null infinity, and you study it at, say, u equal to minus or plus infinity. I mean, he studied it just at minus infinity, but you could also do it at plus infinity. Then it had the following decay. So it decayed very slowly, and it decays as 1 by u. And so now this argument that he gave for this decay was for very slowly moving particles, but you could generalize this to arbitrary configuration of incoming particles also. And now here is what is so you can ask, so what is the big problem about this, because it's simply a consequence of equation of motion. But it turns out that Christodoulou's main argument was the following, that if you now assume that the metric at spatial, if you go large distance from spatial distance from the source, if the metric has no problem, it's completely nice, then the fact that this shear falls off as 1 by u at asymptotically in u, that peeling equation we wrote down, which is this one, is generically violated. And so to be more concrete about this, he showed that one of these wild scalars will decay not with the polynomial power of r, but with some which will go as log r by r to the 4. And this is really in some sense a problem, in the sense that class of spacetimes where radiation as such log r tails are not our garden variety asymptotically flat geometries, because even if you may be not convinced by these abstract psi wild scalars, but the fact that the psi 1 has this weird decay actually filters down into the asymptotic expansion of a wild scalar has this logarithmic branch cut, then just the metric in larger expansion has these modes, which the first few modes are okay, they are what we would expect, but especially the 4th mode has a log component. So the present, this is a kind of a strange
question.
Is there a question?
Yeah, one quick question. Chi1 is the vector, right?
No, these are all just scalars. I mean, these are just wild scalars. I'm just written them in the yeah, it's just some component of the wild tensor, some particular component of the wild tensor.
I see. Okay.
So this is a kind of a strange thing that we wanted to find a universal explanation for this new event shape, this log mode, but its own presence is telling us that we have to really work very hard to even find possible symmetries of this. We have to revisit the whole idea of asymptotic symmetries because these spacetimes are not asymptotically flat. And these spacetimes have been investigated in great detail by Mark Gieler and Céline Zwickel, and they are called polyhomogeneous spacetimes. So now we have to kind of go back to drawing board and see if what are the symmetries of these polyhomogeneous spacetimes. And okay, one nice immediate respite is that super translations or the BMS symmetries are still symmetries of the spacetime. They preserve. I mean, if you start with a spacetime which has this log mode in the metric, it will not be violated if you have super translation. Which means that the first Aya triangle, or at least the classical side of the first Aya triangle that we discussed, it is not going to be touched by this violation of peeling. And it was also shown that these polyhomogeneous spacetimes have more infinite dimensional symmetries in the sense that the transformations which map one of these spacetimes to a different spacetime which has the same fall-off. And these are really diffeomorphisms of the metric at infinity. So, if you just take smooth diffeomorphisms of the sphere metric, and that will give you some kind of complicated transformation of the metric in the bulk, but they preserve this flatness. It is polyhomogeneous flatness of the metric. And this group of smooth diffeomorphisms is, of course, infinite dimensional. And it's like an infinite dimensional enhancement of the Lorentz group, which is just SL2C at infinity. And so along with super translations, they form a group itself, which is a very large and in some sense complicated group, which is called generalized BMS group and future or partial infinity. And it's something that with Miguel, we proposed in 2015 as a candidate group for gravitational classical scattering. And just to quantify what these symmetry generators are, so the super translations are angle dependent translations in U, and these diffeomorphisms, which are also sometimes called super rotations because they are enhancement of rotations, they are basically parameterized by vector fields on the sphere at infinity. Now, if you want to understand if their corresponding charges and conservation law give us these new event shapes, we have to find, we have to compute charges using some techniques which are called covariant phase space now, but things become very, very hard because this space-time, this metric have these log branches, etc. But it can be done. It's something that will come out hopefully in a couple of weeks or next month. And it turns out that for these new symmetries, one can again compute charge like we did for super translation on a sphere at infinity. And I'm just schematically writing the charge on a sphere at infinity at say when I say sphere at infinity, you go to null infinity and take sphere at u equal to minus infinity, and this charge is roughly speaking given by the angular momentum aspect of the gravitational field, so this Na is again related to these wild scalars, but I'm not writing formulas for this because it's just very complicated. Now, an interesting point which has been known for last few years and especially has been explained by Flanagan and David Nichols is that if you assume peeling and if you assume there is no log terms in your metric or anything, and then if you just evaluate this Na on some solution, then it turns out that if you assume that this new charge, which is in equation 2 here, if it's conserved between future and partial infinity, and if you assume that peeling is not violated, then it precisely gives us a formula, which is the formula for what we call the spin memory. So if you remember when we did the schematic soft expansion, we had this red term, which as I explained was universal in higher dimension, and in 4 dimension, the term was really not robust under long range effects. But if you ignore long range effects, then of course it's a universal term and it really comes from conservation law of this super rotation. So it's comforting on some level that the spin memory is a consequence of some conservation law, but at the same time, it's because the spin memory relies on a very strong assumption which is violated in 4 dimensions. So it's not something we should be entirely happy with. But in general, if you want to relate, when we don't assume that peeling is preserved and we have this polyhomogeneous spacetime, if you want to generally relate these abstract charges in terms of these wild scalars, in terms of scattering data of massive particles, we need to have some perturbative expressions in terms of, let's say, massive fields or massive particles which leak out at infinity. We do not know at this point. It's important to emphasize how to do this in full GR, but we can do it perturbatively. So we can assume that we have a flat space and we do scattering of massive particles and we do perturbative gravitational scattering and then try to compute these charges explicitly in terms of the initial and final momentum of the particles and the fields. And this can be done. This is something that we did came out last month with Sangmin and Andrea. And this charge can, again, schematically, we can write it as two contributions. One is like a matter contribution, which is a contribution of the particles, which go towards the future. And this contribution diverges logarithmically with time. And then there is a contribution of the radiative field of the gravitational field, which is leaking out at null infinity, and that diverges also logarithmically in the retarded time. So this is in some sense, a good and the bad news. Good news in the sense that, okay, we could compute them and they have some sort of a log dependence, but bad news is they are just ill-defined because they are just infinite, because in the end we take t and t to infinity, and then the first term just diverges. And this is a charge. The plus superscript here simply indicates that I've computed them for the outgoing fields, but of course we could do the same computation for the incoming fields. And now this, because they are divergent, we have to regulate them. So we can do a very brute force regularization. Let's say we just regulate both the log divergences in the time and in the null direction with some cutoff lambda. And then both in the past and the future, we will have some regulated charges. And here's the remarkable fact that if we now postulate that these regulated charges are conserved, then in the conservation law, the regulator drops out. Both terms roughly we get log lambda in both sides. We can just cancel it at finite lambda. And then the coefficient of log lambda is precisely producing for us the first log event shape, which is the first Logsdorf theorem, which is this equation 4. So equation 4 may look a little unfamiliar to you, but if I had a log mode, which I wanted to isolate in expansion, I have to take a residue in this way that I have given here with some derivatives in omega, etc. And that gives you kills all the other terms except log omega in my expansion. And it's this equation 4 that comes out of this conservation law of these regularized charges. So, so this tells us that all this work of going to polyhomogeneous spacetimes and looking at new symmetries in some sense may pay off, because they explain universality of this, at least the first Logsdorf theorem. So let me at least summarize what I've said up till now. That so in four dimensions, of course, we have only so far discussed the classical side of these infrared triangles, and the first infrared triangle is of course completely robust in the sense it is simply telling us that the displacement memory is a consequence of super translation charge conservation law in a gravitational scattering. The second one is far more subtle because of even though we are looking at classical theory, there are still infrared divergences as we saw here because of the late time effects. And in fact, to understand the universality of the tail to the memory, we have to look at new class of spacetimes. We have to look at new class of symmetries. But these new class of symmetries are this diffeomorphism in the sphere, and at least the perturbative computation of the charges for the symmetries precisely gave us this the Logsdorf event shape. So okay, now let me just briefly discuss. Actually, I have time, but yeah, anyway, let me just discuss this quantum part of the story, which I haven't even touched. So in some sense, the most fascinating part of this infinite triangle are really the factorization theorem in the amplitudes. It may seem like an oxymoron that in 4 dimensions we are talking about amplitudes, because even in effective field theory, strictly speaking, amplitudes do not exist because they are infrared divergent. So you may ask, what do you mean by factorization of some amplitudes which are ill-defined? But factorizations are clever in the sense that they are really statements about ratios of the amplitudes. And the remarkable fact is that if I consider a scattering of n particles with one graviton with momentum k, and I look at the ratio of that scattering amplitude with a scattering of just the n particles, and I do a soft expansion in the frequency of k, then the expansion terms that I come, even though this mn plus 1 and mn are both infrared divergent, the divergences are same in both of them. They cancel, and you get a infrared finite, infrared safe soft expansion, which I have indicated in this equation on the right hand side. Of course, the first term in this, which is n equal to -1, is very well known. It's called Weinberg's soft theorem. But these other two terms, which are I feel like quite rather remarkable, and they were computed exactly by Bishwajit and Ashok. They as you can see that the n equal to 0 terms again goes as a log omega. So it's kind of tied, it's somehow tied to the tail to the memory in the classical radiation. And the second term goes as omega log omega square, which was also, I mean, the dependence on omega is very similar to the dependence of the second log mode in the classical radiation. But these terms, their forms are different. These terms are not exactly the same as the classical logs of factor because of course they are quantum corrections, but they are exact and they are infrared safe. So that's a remarkable statement. Once again, they are exact to all orders in perturbation theory in the Newton's coupling. There are conjectures that similar higher order logs of theorem should exist, but the explicit proof has only been done up to n equal to 1. So that's why I have only written up to this point. The relation with the infrared triangle, okay, so we know that if you just take classical limit of the Weinberg's theorem, in the sense that if you take large bodies and you look at the classical limit of the amplitudes in the way Emil talked about, for example, and you look at the what happens to the leading soft radiation, it turns out that it precisely gives us a displacement memory effect. There's a lot of progress now in showing that the classical limit of the first quantum logs of theorem is it matches with the tail to the memory, but this, to my understanding, it has only been checked up to some order in the expansion in the Newton's coupling. Although we should remember that all these soft factors are non-perturbative; they are exact to all orders in the coupling. But okay, so this is first tab at as far as the quantum logs of theorems are concerned in understanding their universality in terms of some symmetries. So let me actually conclude. I'm almost done. So these hierarchy of event shapes are interesting class of non-perturbative radiative observables, and they are completely analytic in terms of they're completely expressible in terms of initial and final momenta and angular momenta spin of, for example, of the scattering objects. And as we saw, they can be used to probe interesting aspects of classical and quantum scattering. And I just wanted to mention something that there are several properties of these which are rather remarkable and not physically understood. So just to give you one example, if you consider classical scattering involving, say, merger, in which two black hole comes and they collide and they form one single object, one black hole, but such that most of the energy and angular momentum is carried by the gravitational waves, then the first tail to the memory, the first log omega term, exactly vanishes. This is something that we observed in a toy example with Ashok, and then it was proved more generally by Vishwajit and Ashok a few years later. And this is very similar to morally similar to the surprise that Raphael talked about the love numbers of black hole, in the sense that their vanishing is something which tells us that maybe there is a deeper structure to the gravitational scattering. And similarly, in this case, the fact that for some class of scattering, this tail exactly vanishes, maybe hints at something deeper, which we do not understand yet. Although infrared triangle is an abstract idea, and you may think it's kind of useless to just put some pictures with some words, but one good thing it does is to forces us to confront infrared issues that plague both classical and quantum scattering head-on, because we are forced to, if you want to understand universality of these factorizations together, then we have to look for some symmetry, etc. And it in fact leads to some potentially intriguing perspective also on the asymptotic states of quantum gravity, which like states which have memory, unlike the Fock states of gravitons, which are just finite energy states, not zero energy states. And there is some recent work on how these novel states which have memory may lead to some infrared at finite asymmetries of quantum gravity. So okay, so I will end with that, and thank you very much for listening.
Thank you, Alok, for the very interesting talk. There were quite a few interesting questions within the talk. That was great. We still have time for some questions. So, yes, Kansham, please go ahead. Good to see you and TRG both. So,
yes,
I've been attending most of the talks. In between one or two I skipped, but
yeah, yesterday I sent you a hi in a personal chat. I think you missed it. But anyway, good to see you. Please go ahead.
Yeah, a couple of somewhat naive questions. One is related to the Pistotoli result that we explained, that
yes,
the peeling property depends on the spatial infinity being smooth. Is that
yes.
I mean, so what is sacrosanct about spatial infinity being smooth?
Yeah. That's a very good point. So that was Christotolo's original argument. His argument relied on the fact that that you have some you have some source in the far past which is also subjected to Coulombic interaction. So you have some particles, but they are not free even in the far past because of the long range effect of gravity. Then they are emitting radiation, and then you just see that this shear goes as 1 by u. So that's just computing quadrupole radiation. So that's okay. And now the point is that you want to now relate this presence of 1 by u mod in C with the behavior of wild scalar. And in order to connect the two, he had to assume something about metric at spatial infinity. And he assumed that there was a regularity. So this recent work of Kerberger et al., they seem to relax these assumptions and try to go beyond it. But Christodoulou, for him, it was important that to show that this 1 by u modes violate peeling, he had to assume regularity of the metric at large distance when you go, as you go towards spatial infinity. Yeah. So
but
I
would you
think
say that, sorry.
Yeah.
But would you say that moment massive particles are inward, peeling is going to be off?
Yeah, so what is absolutely clear is that
without assuming spatial infinity.
Yeah. This is something I don't know. So what is interesting is the following that I did not have much time to get into. That so the issue whether peeling what is unambiguous is the behavior of shear when you have massive sources. So that is at late u it goes as 1 by u, that's unambiguous. Now whether if you say that okay, maybe something weird happens at spatial infinity which saves peeling, that would imply that this presence of 1 by u modes in C will not induce any log terms in the metric expansion. Or then if that was true, then you could look at asymptotic symmetries for that class of spacetimes, which are the usual,
Right.
spacetimes. And
Right.
there the symmetric group is BMS and this generalized BMS. Now, if you have polyhomogeneous spacetimes, which is what will happen if your peeling was violated, even then the symmetric group is generalized BMS. So what is interesting, at least from our perspective, is that irrespective of the rigorous nature of peeling, the conservation law itself is sensitive to the behavior of shear at large u, but it is not sensitive to the violation of the presence of peeling. So you know what I'm saying? Like although we had to show that when peeling is violated, these symmetries exist, they turn out to be exactly the same as when the peeling was assumed to be not violated. So that's a good. I don't know, Shyam, if that.
Well, to some extent, I will discuss with you more because I need to understand it properly first. I have another small question. There was the last part you mentioned that although the infrared can be equal to 4, the amplitudes are infrared divergent, but the ratios are okay.
Yes.
Now the question is, these are
ratio in the soft expansion.
Yeah. The point is these two when the moment are sharply defined. But if you were to do the calculation with wave packets, would that how will the result reflect?
No, that won't change this result because
course,
this is just.
It will manifest in some other form. But it's not an artifact of sharpness of state.
No, it is not. It is artifact of IR divergence. Yes. So if when I just briefly indicated that we want to take classical limit of these amplitudes for which we will have to use wave packets. So so the point is that I just wrote it as we always do in quantum field theory to write this amplitude with sharp. Yeah, but we always assume there are wave packets, of course. Yes.
Okay. Thanks.
Thank you, Alok. So there was another person whose hand I don't see now, and then it was TRG.
Okay, I'll ask now.
Sure.
Is it okay?
Oh yeah, of course. Go ahead, please, TRG.
Okay, I have two simple questions. You mentioned about the infrared problem and then regulating it.
Yes, for the charges.
So
yes.
what is the meaning of that regulator?
No. So yeah. I mean that's just IR infrared regulator. Like it's just let me go back. So this is the late time or large volume divergence. So we are simply regulating it with some cutoff in space time. Like we are putting space time in a box with some cutoff lambda. It has no so only quantities which are independent of lambda are interesting for us. And so it is good that the conservation law as an equation is independent of this cutoff. But to define these charges and define the conservation law, we have to first regularize them. So
the moment you introduce this cutoff, or the space-time cutoff, you will be breaking some symmetries. The regulator breaks some symmetries.
Yes. I mean, I did a brute force here just for explanation. We could do it in a more sophisticated way using dimensional regularization, which will not break Lorentz symmetries. But of course, you are right that these are these are not well defined in the limit of lambda going to the cutoff going to 0. They are divergent. So what my claim is that these charges have no meaning, but the corresponding conservation law gives us the infrared finite event shape, because this f log, which was this coefficient of log omega in the classical radiation, that is completely infrared finite. So that's all I'm saying. Yeah, but absolutely you're right that the charges themselves are not measurable; they are just infrared divergent.
Okay, I have one small question. You were saying words like quantizing gravity, quantum gravity. What is
I
meant
meant
by
only
that?
in the amplitude, in the sense of. So the point is that because these are asymptotic, I mean, the point is that because these are infrared symmetries of the classical scattering, you would expect that in the infrared, we would not need to understand the deep ultraviolet quantum gravity, and so we expect them to be symmetries of the quantum gravity also, because they are asymptotic symmetries. And indeed, that for super translation now we know it's true that it is not broken by quantum effects, super translation symmetry, and in fact the water entity gives us the Weinberg's-Hoff graviton theorem. So that's all. I mean, these are because these are in the infrared, right? So we are agnostic about the string theory or deep UV theory. Yeah.
Okay, fine. I'll talk to you later.
Yes.
Thank you. Thanks for the question. Thanks, Alok, for the answer. We have next Sona. Please go ahead and ask your question.
Yeah, so I have a quick question. So when you talked about this large gauge transformation, so can it become physical at the boundary of the theory? So is there any possibility that this becomes physical and there is a change in the charge algebra?
It is physical because the charges are the observable. So for example, super translation charge is the displacement memory, which we know is observable, right? So
Yes,
if it was not physical, then the charge will vanish, right? I mean, the one way to distinguish symmetries from gauge is to just compute Noether charge, and for genuine gauge transformation, Noether charge would just be 0.
No, so actually I'm talking about this age modes. If there are some age modes like in large gauge transformations doesn't like it becomes physical at the boundary, then there should be some age modes which interferes with this algebra that we were talking about. So is there any change in algebra due to this large gauge transformations, or it is due to this large gauge transformation we have this?
Which algebra and
The charge algebra we were talking about, this Q.
Yeah. No. This is a very good question. So there we have to discuss in more detail. I mean, the charge algebra of GBMS in classical theory closes. It closes and it represents the algebra of the vector field. This is something that Miguel and a student Peraza showed in a beautiful paper a few years ago, and then there is some work by Geoffrey Compere and others also. So classically, the charge algebra represents the algebra of vector fields of GBMS. This we know. I mean, we have to do a lot of work to prove it, but it has been shown. I'm not sure if that was yes.
So
there are
generally
everything. Yes. But
so generally, when you have fields in this case, so these fields are the boundary conditions are chosen in such a way that these age modes are not there. So if there are age modes, like is there any change that can happen in this algebra that you are defining with these charges? So that's the point.
No, I'm not sure. I mean, we are not. I mean, we are not. The boundary conditions are really not that much up to us here. That's the point, because we are looking at scattering. We are not looking at external infinity in isolation. So we know that the shear field has a particular behavior as you go, for example, U2 plus infinity. So it has some mode which is decaying as 1 by U, one mode which stays constant as U to the 0 at large U. So we have no choice. So whatever boundary conditions scattering gives us, whatever boundary conditions outgoing radiation give us, we choose that. I mean, that is really the heart of many of these problems, that the fact that if I throw away this 1 by U modes, my life would become very simple. All these divergences in this charge in this slide will disappear, and I will recover spin memory, etc. But once I don't do it, and I really stick to the boundary conditions that radiation or Bishwajit and Ashok's theorem tell us, then all these other issues come up. So we are really not we are not forcing any
okay, so that's actually natural. I see.
Yeah, it's natural. Yes.
Okay, thanks.
Thank you. Are there any other questions for Alok? All right. If not, let's thank Alok and all the other speakers of today and as well as yesterday. So